Hi, welcome to this video tutorial in our Deep Learning for Geospatial Data Analysis series. In this tutorial, we are going to build and train a simple deep learning model in order to classify satellite images from the EuroSAT dataset. So by the end of this video, we are going to visualize the learning progress and the model prediction. So we are going to use TensorFlow and Keras in this model. So let's get started. So first, we are going to load the EuroSAT dataset using the TensorFlow datasets. Okay, and this dataset contains labeled satellite images representing 10 land cover classes. So to keep things small and fast, we will just use a subset of 500 images. So the Euro dataset is a widely used benchmark dataset for training and evaluating deep learning models for land cover classification. So it consists of 27,000 satellite images, which are patches derived from Sentinel-2 images. So each image measures about 64 by 64 pixels, and this dataset is very important. Because it can be used to test a number of the convolutional neural network models, and it is also a well-balanced data set, so containing a number of land cover classes, for example, residential areas, forest, rivers, and agricultural fields. Right, so what we are going to do here, we are going to first define a processing pipeline. So we define a function, the preprocess function, in order to resize the images, and then we cast them to float, and then we make sure that they are normalized so that the pixel values are between 0 and 1. So this kind of standardization improves the training stability. Right. So next we are going to compile the model. Okay. So here we are going to use the model that we previously created in the previous video tutorial. So remember, we used a sequential API, a sequential Keras API to create the CNN model. So we are going to use that model now to do the classification. Right. So we compare the model with the Adam optimizer. And then we have the loss. We are going to use the sparse categorical cross entropy. And for the evaluation metrics, we are going to use accuracy. So here the Adam, this optimizer, is refers to the adaptive moment estimation. So this is an optimization algorithm which is commonly used for deep learning models. So it combines the best features of two other popular optimizers. That is the ADA, GRAD, which is adaptive learning, which adapts learning rate for each parameter, and then the RMS prop, which scales the learning rate using a moving average of recent gradients. So this is a combination of Adams, a combination of two powerful optimizers, that is the undergrad and the RMS probe. And for the loss function that we are going to use during training, it is going to measure how well the model predicted the then cover class probability. Okay, so it's just measuring how well the predicted class probabilities matches the true class labels. So this is the sparse categorical cross entropy is used for multi-class classification problems. So here it just expects integer labels, that is from say 0, 1, 2, 3, 4, 5, 6. And for the accuracy here is just calculates the percentage of correct predictions. But then after that, we are going to train the model. Okay, this is trained on the processed dataset. Remember the processed dataset, trained DS, and it runs for 5 epochs. So using the fit method. Okay. So as I said here, this one trained DS representing the training dataset, and this is going to be used to update the model internal weights through back propagation. So this parameter, the epochs here, this means that the model is going to iterate over the entire training dataset 5 times. So this allows it to gradually improve its predictions. And here the validation, this validation variable is this argument specifies that we have a separate test dataset that is used to evaluate the model performance after each epoch. So this is done without updating the weights. So this helps to monitor for overfitting or underfitting of the model. So the results of this model training, such as loss and accuracy for both training and validations, they are stored in this object here, this history object. Okay, so these results are stored here. So later we can visualize and analyze how the model is performed. Okay, so based on this history, we can now create a plot that shows the model accuracy, that is the training accuracy, and the validation accuracy. So this is just simple. If you want, you can also show the loss, but here we're just working on the validation and the model accuracy and validation accuracy. Right, so if we run this code, we are going to run the model. So this is quite a small data set, and also the epochs are not, we don't have many epochs, we only have 5. So this is the results, and this is the graph that we can plot. So we can see that we have a gradual increase in the training accuracy, and the same for the validation accuracy. And then as we move, we almost have this two, the training and validation accuracy coming together. So it looks like the model is doing a good job, and we are not experiencing any major problems in terms of the overfitting or underfitting. So hopefully, if we run many epochs and if we include many assembled datasets, we are going to get an improved performance. Right. After that, we can visualize the predictions that the model has done. So these are the predictions. So here we have these labels showing true. So this is the original, that is a forest, and then this is the predicted, that is forest. So if these are the same, then the model has done a good job. So for forest it's okay, and then for residential we can also see that the model managed to predict correctly. And then for the herbaceous vegetation, we see that the model is predicted permanent crop, so it has failed to identify the herbaceous vegetation. And then if we look here, again for residential, we don't have any problem. Same for forest. But then if we look at the annual crop, it seems the model failed because it has predicted the river, which is wrong. And the same for the river. So it looks like the model also has failed to predict river because it has predicted as highway. So for the annual crop, this is fine, and for the forest, this is fine. Right. So this is all about this introductory series of on deep learning for geospatial data analysis. So hopefully this is going to encourage you now to or to dive further into more advanced tutorials on deep learning. Right, so what we are going to do from the next lab, we will be using the data sets, for example, that we used in the previous series on machine learning for geospatial data analysis. For example, we are going to start with the modeling above ground biomass density using a simple sequential deep learning model. So in the next tutorial, we will start by preparing the training data set, and then after that we are going to use a sequential deep learning model in order to predict above ground biomass density. So thank you very much for watching this tutorial. See you in the next one.